Weighted bipartite matching. Recap of previous lecture. We have discussed conic Eger-Vary theorem, independent sets, covers, that is the vertex cover, edge cover, maximum bipartite matching, augmenting path algorithm. Content of this lecture. In this lecture we will discuss weighted bipartite matching, transversal, equality subgraph, and a algorithm which is given for weighted bipartite matching is called Hungarian algorithm. Weighted bipartite matching. In the last lecture we have seen the maximum bipartite matching, or we have also seen the maximal cardinality We have seen earlier the maximum cardinality matching algorithm which we have seen in the last lectures. We will generalize it. If we take a graph which is a weighted bipartite graph, we seek a matching, a maximum matching of the maximum total weight, and that is why it is called as a weighted bipartite matching. So, the results on a maximum bipartite matching will now generalized to the weighted graphs, and in this we seek the matching of a maximum total weight. Hence, it is called a weighted bipartite matching. So, here we are given a graph again of that particular complete bipartite graph KNN. If the edges are not present, then we will add the edges having the weight zeros to make it as KNN. Adding this particular extra edges of a weight 0, we are not going to change anything in this particular problem setting, that is the solution is not going to be changed here in this case. So, we can do that. Since we consider only the non-negative edge weights on the edges, some maximum weighted matching is a perfect matching, and thus we seek the perfect matching, and we will solve both the maximum weighted bipartite matching and its dual in this particular problem setting. So, we will see what its dual is. Or in last lecture we have seen that the dual of a maximum matching problem was the vertex cover. So, it is a minimum weight vertex cover, and that will be basically solving the problem of maximum weighted bipartite matching here in this particular problem setting. So, let us see the example of a problem setting. So, here this particular graph, you see that it is KNN graph, and these edges which were not there, they were added with a weight 0 to make it as complete bipartite graph. Now, all other edges were having the weight. So, we have now obtained a weighted bipartite graph, and now we will seek a perfect matching in this particular problem setting of a maximum total weight. So, this kind of problem will arise in many practical situations. One such situation we are going to see here in this particular problem setting, that is, a farming company will own, let us say that n farms and n processing plant, and each farm can produce the corn to the capacity of one plant. So, the profit that results from sending the output of the farm I to j, we are going to represent it so this is, let us say, a farm and this is the plant. So, let us say that if it is a farm I and it is sending its produce to the plant j, so there will be an edge, and the weights assigned to this particular edge is wij, and this particular wij will indicate that the profit, if the farm will send its produce to the plant, then the total profit earned will be mentioned as wij. So, not only the edges we are going to add, we are going to add its weight also in this particular problem setting. Now, this particular company wants to select those edges which will form a matching, which will matching of a total maximum profit. Furthermore, the government claims that too much of corn is being produced, so it will pay the company not to process the corn. The government will pay, let us say, a unit ui if the company agrees not to use the farm I, and vj if it agrees not to use plant j. So, in the earlier problem setting, we have seen that there is an edge of sending I to j. Now, this particular I and j will also add an weights on the vertices. So, the government will pay ui if the company agrees not to use the farm I, and it will use vj if it agrees not to use the plant j. So, it is ui and it is vj, and this is wij. Now, there is a decision here in this case, ui plus vj, that means to stop a production I and j should get a money, and that is equivalent to ui plus vj, and this particular money is compared to wij. Now, the plant who is making the profit, if it is using the produce of a plant or a produce of a farm and manufacture it, getting the profit of wij, but if it is not doing it, it will get ui plus vj. Since this particular value is less, so it will try to, the plant will try to make a profit, company will make a profit and it will do the production. So, in order to stop all the productions of a corn, the government must offer the amounts which are basically at least wij, that means ui plus vj is at least wij. Now, then government wants this particular value is to be minimized. So, it is a dual problem, that means the company wants to make the maximum profit and the government wants to stop the production with the minimum cost bearing. So, it is a dual problem, and we are going to solve this duality problem using weighted bipartite matching. So, the algorithms and all those techniques which we are going to cover, which will solve this kind of problems. So, all these things we will discuss again after seeing the details of the algorithm. Let us see some of the definitions. So, transversal of n by n matrix consists of n positions, one in each row and one in each column. So, it is a n by n matrix is called transversal if we can identify n positions. That means, if it is, let us say in this example, in every row there is only one particular element selected, in this row also there is one element selected, in this row also is one element, and so on. So, in each row one element is selected, similarly in every column also one element is selected. So, in this way this particular matrix will have n entries earmarked in n by n matrix, and this particular setting in which we could identify n different positions in a n by n matrix, then it is called a transversal. If not n positions are identified, but following that every row or every column should basically fix up one position and not all n positions are identified, then it is called a partial transversal. These two terms which we are going to use it in this algorithm or in this discussion. So, finding a transversal with a maximum sum is nothing but an assignment problem. So, this is the matrix formulation of a maximum weighted bipartite matching, where the non-negative weights Wij is assigned to the edges of the complete bipartite graph KNN, and this will formulate the assignment problem. So, we seek in this particular problem setting a maximum matching or perfect matching to maximize the total weight, that is W of this M. So, this particular transversal we have to identify, so that when these particular n positions, if we sum, that will be having the maximum total weight, and that also can be represented in this particular graph. So, it is a matrix version of a weighted bipartite matching is called an assignment problem. Now, we are solving the dual problem. That means, when we find out the maximum matching of maximum total weight, then we are solving a minimum cost vertex cover also. So, both are dual problem. If we solve maximum weighted matching, then we are going to solve the minimum weighted cover, or if we are solving the minimum weighted cover problem or given, then we are going to solve the maximum matching of a maximum total weight. So, with these weights, a weighted cover is a choice of these particular label. So, these are the labels which we call them as UIs, and these labels on these columns is called VIs. And if we sum them, that means all UIs plus all VIs, then it will form a cover, and that is called CUV cover. And this particular CUV cover is nothing but a summation of all UIs and summation of all VIs. We want to find out this particular cover of a minimum weight. That is finding a cost of a minimum weight cover in this particular problem setting. This duality of weighted matching and a weighted cover problem is expressed using a lemma. So, let us see the lemma. For a perfect matching M and a cover UV in a weighted bipartite matching G, also is represented as C of uv is equal to the w of m if and only if m consists of the edges xi, yi such that ui plus vj is equal to wij. In this case m and uv are the optimal when ui plus vj is equal to wij. Let us see the details. Since m saturates every vertex, summing up the constraints ui plus vj is at least wij that arise from the edges which will yield c u comma v and w of m. That means the equality must hold in each of n equalities which are summed up. Finally, when c uv, that is the cover, is at least the weight of the matching for every matching, and every cover, when this cover is equal to the weight of a matching, which will imply that there is no matching with a weight greater than c uv and there is no cover with a cost less than wm. That is, this particular situation when it will arise, this is an optimal situation. That means when we reach to this particular situation, that will tell us that we have identified a maximum weighted matching with a cost of minimum vertex cover. Similarly, minimum vertex cover which we have obtained with the cost of a maximum weighted matching, both are equal. Let us see more definitions. Equality subgraph. Equality subgraph is represented as GUV for the weighted cover. UV is the spanning subgraph of a bipartite complete graph KNN whose edges are the pairs xi, yi, yj such that ui plus bj is equal to wij. So, in the cover, axis for I and j is nothing but ui plus vj minus wij is an axis. We will see this particular representation further. Now, in this particular graph, which is called basically the equality subgraph, we have to seek for a perfect matching, and if this particular perfect matching with the weight equal to the CUV is equal to the, so the matching of that weight if we are attained, then basically it is a optimal solution. Otherwise, we find a matching M and a cover Q of the same size by using augmenting path algorithm, and we seek a larger matching in the equality subgraph and change the matchings to get a maximum matching, and we iterate so that we will basically obtain that maximum matching of a given graph, and this is done through an algorithm, and that algorithm is called Hungarian algorithm, which is named in the honor of Koenig Egervary, who was Hungarian, and this algorithm was identified by Kuhn in 1955 and Moncrief in 1957. Both they have given together this independently these algorithms, and this algorithm is basically named as Hungarian by because Koenig's Egervary theorem on which this algorithm is based. So, in the honor of Koenig Egervary, who was Hungarian, the algorithm was named as Hungarian algorithm. Input to this algorithm is a matrix of the weights on the edges of KNN with the bipartition that we have already told. Now, the idea of this algorithm is to iteratively adjust the cover until the equality subgraph has a perfect matching. So, duality property will ensure that a perfect matching or a matching of a maximum weight has been achieved. So, initialization in this algorithm will do let uv be the cover such that ui, that means all the ui's are nothing but the maximum of a particular row in this particular matrix having these weights Wij and Vj, that means on the columns the cover will become 0. Let us see this. So, here we can see Ui's Uij, that means in this particular row this is the maximum one. So, in every row the maximum value is being taken up as the cover U. Similarly, in all the columns it is initialized to 0. So, these particular values will give the cover. So, having initialized the cover, now we have to see the iterations of Hungarian algorithm. Now, in the iteration we find a maximum matching M in that equality subgraph G U V, U and V which we have initialized and formed. Now, if M is a perfect matching, then we stop and report M as the maximum weighted matching. Otherwise, what it will do, since Q is the vertex cover of size M in GUV, so let us find out the set of vertices of this vertex cover on the X partite set as R, and the set of vertex cover on Y it is called as T, R and T. Then the next step in this algorithm is to find out an epsilon. So, if let us say that it is X and this is Y, let me explain you. So, here there is a T and there it is basically R. And all other nodes are basically touching them like this. So, T plus R together will form a vertex cover that is called Q. Here we have to find out an edge this way. This is Y minus T and this is X minus R. We have to find out an edge which is crossing from X minus R and touching another vertex in Y minus T, and we will find out adding this particular edge is possible if we decrease this value by minus epsilon and increase here the value of U by increase the value of Vj by epsilon. Here we have to increase and here we have to decrease, then only this new edge can be entered into a matching. So, epsilon will be ascertained with Ui plus Vj minus Wij for these values, that is for X minus R these elements and for Y minus T these elements, and we will find out the gap, that is Ui plus Vj minus Wij. We will find out an epsilon and then we will reduce Ui's which are there in X minus R, that means these sets with these values minus epsilon. Similarly, we are going to increase the values of Y minus T by an epsilon. So, epsilon is to be increased here in T. Now, then we will form a new equality subgraph in this particular modifications by epsilon, and then we will repeat these iterations. Let us take an example. We have initialized to U and V, then what we have to do? Then we have to find out equality subgraph. In equality subgraph, this is going to be reduced within axis weights. Let us see the entire thing in this particular problem setting. So, here in this particular example, let us say this is the KNN and the edge weights are given, and let us initialize in this particular row it is 6, it is 7, then it is 8, then it is 6, then it is 8, and on the columns is going to be initialized. So, this is the initialization of Vj's is 0 and Ui's is the maximum of the edge weights in every row. Now, we will find out the equality subgraph. So, excess values we have to basically say 6 minus 4 is 2, 6 minus 1 is 5, 6 minus 6 is 0, 6 minus 2 is 4, 6 minus 3 is 3. So, just see that 2, 5, 0, 4 and 3, that means whatever we have done the modification is already given in this particular matrix. Similarly, all other rows and columns of the remaining matrix can be done. Then in this particular equality subgraph, we have to find out a cover. So, for that we can draw the equality subgraph. So, in this particular equality subgraph, that means wherever zeros are there, that means in the first row. So, wherever 0 is there 1, 2, 3, so it is at this end. So, we are going to add an edge. Similarly, this edge will be added second row and 1, 2, 3, 4, 1, 2, 3, 4. So, this particular edge is added. Similarly, this edge will be added, and then this edge will be added, and finally this edge will be added. So, from this particular graph we will obtain an equality subgraph of all the elements which are basically placed with the 0 values. Now, we have to find out a cover. So, in this cover we can see that this particular vertex will cover these two edges, this vertex will cover two edges. So, these two 1, 2, 3, 4 edges are covered by these two vertices, and this particular vertex will cover this edge. So, all the edges are covered with 3 different vertices. So, the cover on y side we call it as T, the cover on x side we call it as R. So, we can draw like this. So, the remaining part what we are going to see, we have to find out the epsilon is the minimum value of these remaining part. So, these remaining will be from x minus r and from t. So, here we are in t we are going to increase with the epsilon value, and here we are going to decrease with the epsilon value, and epsilon we have to find out of them. So, from this particular column, this column and this column, if we see what is the minimum value, so minimum value is 1. So, epsilon here becomes 1. So, 1 will be reduced from these values. So, they will become 1, this will become 4, this is not going to be touched. So, this will become 2 and 1 will become 0. Similarly, 3 will become 2 and 2 will become 1, 4 will become 3 and 2 will become 1. Similarly, 2 will become 1 and this 2 will become 1. So, it will be increased the values to t. So, here in this particular 2 t's, that is 4 will become 5 and 3 will become 4, and that is all. So, this will become the equality subgraph, and also here on these particular values also decreased minus epsilon, and this here will be increased with epsilon. So, here it will become 1 and here also it will become 1 wherever t's are there, 2 t's are there. So, 2 1's will be there, and here 6 will become 5, it will be decreased, 7 will become 6, this is untouched. Why? Because r is there, and 6 will become 5 and 8 will become 7. So, this is all completely explained. So, this becomes an equality subgraph. In this equality subgraph, again we have to draw a equality subgraph. So, equality matrix it is called, and we have to draw equality subgraph. That means all zeros, wherever zeros are there, we have to place an edge. So, just see that only this edge is extra appearing and all other zeros are same. So, one more 0 is appearing here. Why? Because when 1 will become 0, so only this particular extra edge will be there. That means from second to this particular edge is represented over here. Now, in this equality subgraph, again we have to find out the cover, the vertex cover. This particular vertex will cover these two edges, this vertex will cover these two edges, this vertex will cover these two edges. So, you see that from R all the vertices will be basically covering. So, 3 vertex will cover all the edges. So, this will become T. Now, we have to process as we have processed here. So, there will be 3 T's. Now, we have to find out the epsilon, and so epsilon, if we see, it will be again 1. So, 1 minus 1 is 0, 4 minus 1 is 3, then here 1 will become 0, 6 will become 5, 6 will become 5, 4, 1, 0, 0, 2, and here also 4, 5, 7, 4 and 6. Similarly, here it will be all T's are there, then plus epsilon will be added, 1 plus 1 is 2, 1 plus 1 is 2, 0 plus 1 is 1. So, we have obtained this particular graph, and in this particular graph we will do the further processing. Let us see the steps. Yeah, this will be a final graph. So, in this final graph we can see that we have to using this particular equality subgraph we will obtain the matching. Let us see, go ahead. Now, wherever zeros are there we will mark in the first row 1 and 2. So, 1 and 3, then second one is first one, then last 2. Then third one is the last, then fourth one is 2 and 3, fifth one is 2 and 4. Now, we have to find out the matching or the covers. So, we can basically see that this particular vertex is having only one edge. So, this particular edge definitely will be there in the matching. So, having contained this particular edge in the matching, so this particular edge will be not there in the matching, and once this particular element is there in the matching, then entire row, that means all other zeros. So, this 0 is eliminated and this column is also eliminated. That means this row and this column has now one 0 included, this 0. Similarly, if we take this particular row, we have 2 zeros, we have to select one of them, and this particular column we have to select one of them. So, in this particular row this 0 is selected. So, if 0 is selected, then this particular column will go out and this column, this row will also go out. So, this will not be there, this will also will not be there in the matching. So, the remaining one is this one. So, there is only one 0 remains. So, here this 0 also will be there in the matching. So, if this 0 is in the matching, so this 0 will be eliminated. Now, there comes this particular column, this 0 is included in the matching. So, having included this particular matching, only this particular matching remains. So, if we see through the diagram the matching, so 1 will be matched to 2, then 2 will be matched to 1, this edge, then third will be matched to the last edge, third one will be matched to the last edge, then fourth will be matched to the second one, and then sixth, that is the last one, will be matched to last but one, this particular. So this will become the matching, and we can find out the total weight. Total weight of this particular matching will be 0. That means 1, 2, 3. 1 to third is 6 plus 5 plus it is 8, then it is 4, then it is 8. So it comes out to be 31. So we have identified the maximum matching using Hungarian algorithm, and we have also estimated the cost, that comes out to be 31. So if we add the vertex cover which is obtained, this is 5 and plus 16 plus 5, that becomes to be 31, is given by the minimum vertex cover, and this is the matching. So here when the problem converges to the optimal, then basically the vertex cover is equal to the matching, and both are 31 here in this particular example. Let us take an example which we have started, that is the farming company will own n plants and n processing units. Let us see this dual formulated problem, how we are going to solve using Hungarian method. Let us represent this particular graph GUV having n farms and n plants, and let us take all these particular steps of this particular graph. So this is basically the initialization. So here on the vertex side we are initializing it to 0, and here you see that this is the maximum. So maximum is kept over here, and it is 7 is the maximum, 8 is the maximum, 6 is the maximum, 8 is the maximum. So this is the initialization part of the algorithm which we have completed. Now this particular matrix which we have obtained is called an access matrix. Now we have to identify the matchings. In this particular matching we have seen this is the partial transversal. Why? Because not all columns and not all rows are being basically covered in this particular matching. So we have to go to the next step, and in this particular step we have identified T and R. So the remaining part we have to identify the epsilon, and epsilon is 1. So if epsilon is 1, then we have to increase this particular value, or we have to increase this value of T, and we have to decrease this value by 1, and also these values are decreased. So this becomes 0, so one edge will be entered, and here these values will be increased. So same thing, whatever we have seen earlier, this is shown in 2-3 more steps. Now we have identified the next particular T, and in the equality matrix we have to identify the epsilon, and it will go to the next steps. So in the next step all these values will become 0, and in this particular equality graph we have identified that you see that in every row, in every column, there is a 0 which is identified. Now we have to identify among these zeros, all zeros in one different row and one different columns are being placed. So that is basically the solution of an assignment problem or Hungarian problem. So whatever we have explained is basically is also proved in this particular theorem. So let us see the details of this theorem. This algorithm terminates only when equality subgraph has a perfect matching. So it suffices to show that it does terminate. Suppose weights ij are rational, then multiplying the weights by the least common denominator yields an equivalent problem in the integer weights. We can now assume that the labels in the current cover are also integer, thus axis is also an integer. So we convert any other given problem in our problem setting of the non-negative edge weights and that to integer edge weights, and we can run this particular algorithm in other problem settings as well. So conclusion, in this lecture we have discussed weighted bipartite matching, transversal, equality subgraph, Hungarian algorithm. In upcoming lectures we will discuss stable matchings, Gale-Shafley algorithm and a faster bipartite matching. Thank you.